Hi, this is Mr. Mack. We're going to talk about roots of a polynomial, or zeros of a polynomial. Now, up to this point, we've had the remainder theorem, the factor theorem, and we've talked about synthetic division and so forth like that. So I'd like to start off by making 4 statements that are equivalent. In other words, if you know any one of these 4 statements is true, you can be assured that all of them are true. If you know that any one of these statements are false, then all of these statements would be false. Okay, statement 1, C is a zero of P of X. Statement 2, C is a solution of the equation P of X equals 0. I mean, that one seems pretty obvious. If C makes P of X 0, when you put C into P of X, it makes the equation P of X equals 0 true. Okay. Statement 3, X minus C is a factor of P of X. And then statement 4, C0 is an x-intercept of the graph of P of X. There is one little quid pro quo thing here. C has to be a real number for this 4th one to be true. If C was an imaginary number, then it won't be an x-intercept. But other than that, these 4 statements are equivalent. C is a zero of P of X. C is a solution of P of X equals 0. X minus C is a factor of P of X. And C comma 0 is an x-intercept of the graph of P of X, provided that C is real. All right, now, the next thing that I want to say is I want to tell you about the fundamental theorem of algebra. Now, that sounds really amazing, doesn't it? Fundamental theorem of algebra. Now, the fundamental theorem of algebra says every polynomial equation of degree greater than 0 has at least one complex 0. Now let me just remind you that the real numbers are part of the set of complex numbers. So when we say it has at least one complex 0, that 0 could be real, and if it has a real 0, then that 0 is in the set of complex numbers, so we could also call it a complex 0. Now, I've got to tell you the truth. This was not what I was taught when I was young, was the fundamental theorem of algebra. What I'm about to share with you is the corollary to the fundamental theorem of algebra, which is what I was taught was the fundamental theorem of algebra, although this is really the fundamental theorem of algebra. But before I get to the corollary, let me just mention that the fundamental theorem of algebra was proven by Carl Friedrich Gauss. Carl Friedrich Gauss is my mathematical hero. He was a man with just an incredible mind, and he saw mathematics with a clarity that has rarely been seen in mankind before or since. Okay, now, the corollary we want to get to. Now, corollary, a corollary, did I spell that right? I guess so. A corollary is a small little proof that's easy to prove once you've got something else. So you see we have the fundamental theorem of algebra, and then almost immediately comes the corollary. And I was taught that the corollary was actually the FTA, fundamental theorem of algebra. Now the corollary says every polynomial with degree n has exactly n complex zeros, including, of course, repeated zeros. All right. So basically, this is what we're going to be making use of a lot in these exercises. If you look at the polynomial and it has a degree of, say, 3, then we're expecting 3 solutions. Now, they might be real, they might be non-real complex, but we're expecting 3. And they might repeat themselves, but we're expecting as many as the degree of the polynomial. Okay, now, another mathematician. Again, the mathematician I'm about to talk about now, I have a tremendous amount of admiration and respect for. He had, I think, the most elegant idea when it came to actually blending geometry and algebra together by taking 2 number lines and crossing them at the origin, and having points in the plane located by ordered pairs. That, in essence, wedded geometry and algebra together into a thing that we call analytic geometry. And it's just an amazingly simple, elegant, and wonderful idea. But anyway, René Descartes also came up with a thing that is called his rule of signs. So Descartes' rule of signs. Now, hang with me on this because this one does get a little bit complicated, but it's not that difficult once you get through it. Okay, let's use as our example f of x is equal to x to the 6th plus 3x to the 5th minus 4x to the 4th minus 6x cubed plus x squared minus 8x plus 5. Okay, now, René Descartes' rule of signs says the number of possible and I want to emphasize possible here, the number of possible positive real zeros of P of x is equal to the number of sign reversals in P of x when, of course, P of x is stated in standard form. In other words, all the terms are written in order of decreasing power. All right, so now let's, further, if that isn't the number of real zeros, then the number will be less than that number by an even number. I'll explain a little bit more what that actually means in just a minute, if you'll just bear with me here. Let me just take all of this and kind of put this together in one grouping. And we'll make it a little bit smaller, so that we can still read it. And let's go back and kind of use this now. It says the number of possible positive real zeros of p of x is equal to the number of sign reversals in p of x, written in standard form, of course. Further, if that isn't the number of real zeros, remember we're calling it the possible number of real zeros. If that isn't the number of real zeros, then the number of real zeros will be less than that by an even number. First of all, what do I mean by a sign reversal? Notice, positive x to the 6th, positive 3x to the 5th, no sign reversal. Positive 3x to the 5th, negative 4x cubed, that is the sign reversal. Negative 4x to the 4th, minus 6x cubed, no change there. There is a change between negative 6x cubed and positive x squared. There is a change between positive x squared and negative 8x. And there is a change between negative 8x and positive 5. So if you count, there's 4 sign reversals in p of x. Now, what that means is we could possibly have as many as 4 positive real zeros for this p of x. If it isn't 4, then it will be either 2 or none. We are not getting 1 or 3 positive real zeros, because René Descartes' rule of signs says, count the number of sign reversals. That's the possible number of positive real zeros. If your number of positive real zeros is less than that, it differs by an even number. So minus 2, minus 4, but not minus 1 or minus 3. So we've got either 4, 2, or no positive real zeros. Now, the bad news is we're only halfway finished with René Descartes' rule of signs. The other part is, it says also, I'm going to clone this, and let's put it down here. So the number of possible, what's going on here? There we go. The number of possible negative real zeros of p of x is equal to the number of sign reversals in p of the opposite of x, written in standard form. Further, if that isn't the number of real zeros, then the number of real zeros will be less than that by an even number. Okay, so what we've got now is, let me group this, make it a little bit smaller here, and let's go get p of x, or f of x, I guess, in this case. And we'll just kind of put that down there where we need it. There we go. Now, first of all, what do we mean by p of the opposite of x? What we mean is we're going to put the opposite of x in for x everywhere we see it. So f of x, f of the opposite of x is the opposite of x raised to the 6th plus 3 times the opposite of x raised to the 5th minus 4 times the opposite of x raised to the 4th minus 6 times the opposite of x raised to the 3rd plus the opposite of x squared minus 8 times the opposite of x plus 5. Okay. Now, let's do some simplifying. When we raise something negative x, or the opposite of x to the 6, we just get x to the 6, because if we multiply a negative by itself 6 times, it goes away. It becomes positive. But the opposite of x to the 5th becomes negative 3x to the 5th. Now, the opposite of x to the 4th is just x to the 4th, so we have negative 4x to the 4th, but we get plus 6x cubed plus x squared plus 8x plus 5. Now, and look at this for just a minute. Now notice what happened was the signs changed on all the terms that had odd exponents on the x, okay? The ones that had even, the terms that had even exponents, when you put the opposite of x in, it doesn't really change it. Okay, so now let's go back and let's take a look at the sign reversals. We have x to the 6th, negative 3x to the 5th. That's the sign reversal. Negative 3x to the 5th to negative 4x to the 4th, no sign reversal. Negative 4x to the 4th to positive 6x cubed, that's a sign reversal. 6x cubed to x squared, no sign reversal. X squared to 8x, no sign reversal. 8x to 5, no sign reversal. So we have possibly 2 negative real zeros. Now, if we don't have 2 negative real zeros, then we will have none. There is no way that we're going to get just 1. All right, now let's put this all together. What they ordinarily ask you to do is they ask you to give the different possibilities for the number of possible positive real zeros, negative real zeros, and imaginary zeros, or in other words, non-real zeros. Okay, so now let's take f of x again here, and we'll clone it one more time and throw it down. Ooh, it's bouncy. Put it down here. Now, what we found was the most positive real zeros, possible positive reals, was 4. Possible negative reals real zeros was 2. And since the degree is 6, that's all of them, 4 plus 2. Now, what we do is we'll make a chart, okay? So the possible positive real zeros, the possible negative real zeros, and the non-real zeros. Now, if we have 4 positive real zeros and 2 negative real zeros, we will not have any non-real zeros because there's a total of 6 zeros, degree 6. Now, we might not have all 4 positive real zeros. We might just have 2 positives and 2 negatives, which would leave us 2 non-real. Or we might have no positive real zeros. We might have the 2 negative real zeros, in which case we would have 4 non-real zeros. Now, we also might have 4 positive real zeros, but no negative real zeros for 2 non-real zeros. We might have 2 positive real zeros, no negative real zeros for 4 non-real zeros, or we might not have any positive real zeros, we might not have any negative real zeros, which would give us 6 non-real complex zeros. Now, this chart right here shows all the different possibilities that René Descartes' rule of signs gives us for that particular polynomial. Now, as you can see, it tells us the possibilities, but it doesn't really tell us in this particular case exactly what we are going to have. Okay. Now, the next thing that we need to talk about is the complex conjugate roots theorem. Okay, now, if a polynomial has real coefficients, then its complex zeros must come in complex conjugate pairs. Now, complex conjugates are numbers, complex numbers in the form a plus bi and a minus bi. In other words, if you have a polynomial with real coefficients, and you know a plus bi is a zero of that polynomial, then you know that a minus bi has to also be a zero of that polynomial, and vice versa. If you know a minus bi is a zero, then a plus bi has to be a zero as well, as long as the coefficients of your polynomial are real. Now, this takes us to the last thing I really wanted to cover in this particular concept video, and that's the concept of how do you write a polynomial that has the given roots. Now, let's take a look at an example. We'll actually take a look at two. Let's say I say, for example, I want a polynomial that has 2, 3, and -1 as zeros. And I want this polynomial to have as small a degree as possible, and I want the coefficients to be integers. All right, well now, I know if 2 is a zero of the polynomial, x minus 2 has to be a factor. I know if 3 is a zero, then x minus 3 has to be a factor. And I know if -1 is a zero, then x minus -1, look what I write, has to be a zero. Now, if I multiply these three polynomials together, I'll get a polynomial with integer coefficients, they'll be real coefficients, of course, of degree 3 that has those 3 zeros. Now, since the corollary to the fundamental theorem of algebra says that in a polynomial of degree n, there will be n zeros, also, if there are n zeros, we can't be any less than 3, so that would be a polynomial of the smallest degree. Now, let's multiply these two together. We get x squared minus 5x plus 6, and we'll multiply that by x plus 1, and that's going to give me x cubed minus 5x squared plus 6x plus x squared minus 5x plus 6. And then combining like terms and writing it in standard form, we have x cubed minus 4x squared plus x plus 6. And that would be the polynomial with the smallest degree, degree 3, that has 2, 3, and -1 as zeros. Okay, now that's all well and good, but what they're going to do is they're going to say, all right, well, what about zeros like 1, -1, and 2i? Now, since 2i is a zero, in other words, 0 plus 2i is the complex number that is a zero, that means by the complex conjugate theorem, 0 minus 2i or -2i also has to be a zero. So I'm just going to put that over here, -2i as well. Now this is going to take us up to degree 4, but there's no other way to get real coefficients without having both 2i and -2i as zeros by the complex conjugate theorem. So now what we'll do is we'll write x minus 1, x plus 1, x minus 2i, and x minus -2i, and we'll multiply them together. These two together multiply to be x squared minus 1. Now these two multiplied together give us x squared plus 4. And so when we FOIL these, we get x to the 4th plus 3x squared minus 4 as our polynomial of degree 4 with the 3 zeros that we were told we had to have. Now, there are a lot of more examples for a lot of this in the solution videos. You have to watch them. This is really very important. But good luck with these. Have fun. This is Mr. Mac signing.